Hey everybody, welcome back. Today we're going to talk about graphics programming on the Apple IIgs, and we can't do that without discussing some of the internal components used on the Apple IIgs, specifically the Mega 2 and the VGC, the Video Graphics Controller. And those are two custom chips used on the Apple IIgs. And we'll also need to discuss the memory map a little bit and how the graphics memory is laid out. And finally, we'll need to start getting into actual 16-bit programming. So far we've been treating the processor like it's an 8-bit 6.5 CO2 processor, and it's time to start taking advantage of the awesome features that the 65816 has, particularly the 16-bit registers. One quick recommendation for today's lesson on graphics. So you go to my GitHub account and print out this crash course PDF that I made for a presentation last year, and it's basically got a cheat sheet of the registers and the layout of the super high resolution graphics display, and it's got other really helpful and useful information, but specifically these diagrams of the graphics layout should really help as you're following along and trying to learn these techniques. So let's get started. The Apple IIgs supports all of the video and text modes that were available for the other models, but it also adds a new mode called super high resolution, and a lot of times you'll see that written in documentation as SHR. So in SHR mode, you can choose 320 or 640 pixels per line by 200 lines high. What's kind of amazing is that you can actually mix and match them on the screen however you'd like, but that might be a bit of a pain to program for. The GSOS desktop and boot screen that you see in the intro to this video uses the 640 mode, the 640 pixel mode, and eventually we'll spend some time discussing that mode, but today we're going to focus on 320 by 200 mode because that's what most games use and it's slightly easier to use. Super high res mode lets you use 16 colors per palette out of 4096 possible colors, and there are 16 palettes. So you've got 16 palettes of 16 colors for a total of 256 possible colors on the screen at once. But the catch is you can only use one of those palettes per line, which means only 16 colors on a single line. And I'd say most games really just use 16 colors, and maybe some had some of the score displays or text on the top or the bottom of the screen in different colors from another palette. So anyway, for those of you not quite familiar with the Apple IIgs, I want to just show off a little bit some of the capabilities of super high res mode with just some stuff I've captured from an emulator. And the first few captures from games are sped up a little bit, but I want to demonstrate the artistic qualities that one can achieve. We'll talk about animation and some of the limitations there a little bit later. So, alright, relax and enjoy some 2GS eye candy courtesy of super high res mode. Okay, so that was just some stuff to whet your appetite. We're going to start with the basics. First thing is, how do we actually turn on the super high-res graphics mode? And if you look in the Apple IIgs hardware reference, Chapter 2 kind of discusses the Mega 2 and the VGC, the video graphics controller. And the Mega 2 is basically an Apple II on a chip, and it just handles all of the displays of the sort of previous Apple II generations. So it does the low res and the high res and the text modes. And the video graphics controller handles the super high res mode. And we enable that using something called the new video register at location C029. So to turn on super high res mode, it's very simple. You just do C029, set it to C1. And you can see that it's still got the GSOS launch screen because I launched Basic System from GSOS. To turn it back to text mode, I just do C02901. And that's it. C1 to turn it on, 01 to turn it off. And what we're really doing is enabling and disabling that video graphics controller to take control of the display and display the super high-res graphics. When it's disabled, the Mega 2 goes back in showing whatever mode was enabled before. The next thing to discuss is where the graphics display is actually located. If you look at page 92 of the Apple IIgs hardware reference, it's got a picture of the memory map, and it shows that all of the super high-res graphics display buffer is located in memory bank E1. And so it's an E1, bank E1, and it starts at location 2000 and continues from there up to 9CFF. So this is the actual pixel data from the screen that we were looking at before. And above that, starting at 9000, are 200 scanline control bytes. So it goes from 9000 to 90C7, and then there's a little gap. And then at 9E00 are the color palettes, which go up to 9FFF. So I'm in bank E1 now. We were looking at the pixel data. I can use this command to write byte 0 to location 2000 all the way up to 9FFF. I don't have to use capitals, but I'll just do it. And then Z to kind of, it stands for zap, but basically it means overwrite these memory locations with the byte 0. So if I look at E1 2000 now, of course those were zeros before, but it looks like a 0 everywhere. And I overwrote the palette data and the scanline control byte data. You can see that basically zapped out our entire graphics display, and that's one way of clearing the display buffer. So now let's talk about how we actually draw something on the display. Okay, really, so far we've been treating the 65816 like an 8-bit processor and using it in what's called emulation mode, where it thinks it's a 65C02. And that's the default state when you turn it on, and that's a default state for the Apple IIgs when you first boot it up as well. So if you want to clear the graphics screen, you could use two 8-bit values and create, self-modifying code or set up zero-page pointers or something like that, like you would if you were programming a 6502. But really, since you're trying to erase 8,000 values in hex, it's just better to go ahead and start using 16-bit code. So I'll show you how to do that now. We'll go ahead and still use the little scratch space at 300. So like I said, the 65C02 mode is called emulation mode. We want to set it to native mode, and you can't directly set the emulation bit in the processor. So what you do is you actually set the carry and exchange it with the emulation bit. So what we want to do is clear our carry and exchange carry with emulation. So now the emulation bit is clear, so it means it's not in emulation mode, it's in native mode, and that means we are running as a 65816 processor. But we still need to do one other thing, which is set the accumulator and the index registers X and Y to 16-bit. So for that, we do a
a rep 30, and that resets processor bits. And if you look at those two, they correspond to the basically what are called the M and X bits. M for the accumulator and X for the index registers. So this would put us in full 16-bit mode. Now if we wanted to clear the graphics screen, we could just do a, load A with 0, load X also with 0, and you can see that if I'm typing in these 4-digit values, so 4 nibbles, it's actually converting it to 16-bit values that it's loading into A and X. And we can also do this now. We know that we want to store it at this long location. So you'll see that it has the bank address for where our super high res screen is, E1, and it starts at 2000. And then comma X is our index register, which of course we're starting at 0. And it automatically created a 24-bit address here. Now since we're in 16-bit mode, we just stored a word, and that means 2 bytes for this processor. So that means that we actually want to increment our index register twice. And we just are trying to store, like I said, 8,000 hex values. Yes, and if we haven't gotten our 8,000 yet, then we branch back to our store loop at 30A. And once we're done with that, we basically have cleared the screen, right? We could go ahead and turn on the graphics screen, but remember we only really need to store 1 byte at C029, so what we could do is we could switch back to 8-bit mode using the opposite of the rep command, the set command, and use this to store, and we're going to do it as though we were in a whatever long bank we may be loaded in, even though I know we're in bank 0 right now. And if I run this, it should clear the screen and return us back to the prompt. Remember, I can do C02901 to turn that back off. So that cleared the screen. Now let's talk about actually setting one of the palette colors. We've just set everything to 0, so everything is using palette 0, and I actually have a pretty good document that shows you the basics of the super high res memory and the overall layout, and you can find this on my GitHub, and it's called gslib. Show the link on the screen there. And basically what we just did was we stored zeros here all the way up from the pixel data through the scanline control bytes to the color palettes. So let's do a quick test. We'll go to the first color of the color palettes, 9E00, because everything should be using that color now. And we'll try and set it to a different color. And here's what it says about that. It says that the basic color layout for each color is 1 nibble per color value using red, green, blue values that you're probably familiar with if you're doing any modern programming where you have red, green, and blue. And normally you might have 0 to 256 or float values from 0 to 1. And in this case we have 0 to F, so we have 16 distinct values for each of the 3 primary colors, which means it's a 12-bit color space or 4096 colors. This color value is not used. It says reserved, but basically you can store 0 there. It's never been used and it's not going to be used. So here's the layout. You've got green, blue, reserved, and red. So if I set this first value to F0, let's see what happens. We'll go back to our emulator. 9E00, F0, and that turned everything to green. Let's try, instead of F0, 30. Okay, just a dark green, right? So I'm just playing with that green value. And if I did 9E00FF, get a light blue, and then I'll do 9E010F. Now we have white. Okay, so see what I did there? You probably can't see my typing, so hopefully you heard what I did there. Let's look at the two values. I put 9E00 and 9E01, right? So I set FF0F, and that was the color white. Okay, so now that should make sense that that's kind of how we write those values. I'm going to go ahead and set it back to 0. And I'm going to go after that, 9E02, and set color 1 to 000F, which means that it should be 0 green, 0 blue, nothing there, and F for red, so it should be red. So let's look. We have our background color back to 0. So now, let's go to 2000, and I'm going to put the value 10. So that is the color 1 up in the very top left. So if you look back at my document that I referenced earlier, this is the pixel data here from 2000 to 9000, and that's basically the layout. Each one references one of the colors of the palette, starting with 2000 in the upper left, and there are two nibbles here, so it's 2 pixels. So if I did 2011, we would have 2 pixels, and so on and so forth. And basically it's a linear display map of index colors like that, going from 2000 all the way down to 9CFF in the lower right. So each line has 320 pixels, but since there's 2 pixels per byte, you know, a low nibble and a high nibble, only 16 color values out of the index palette. That means there are only 160 bytes per line. So the math is pretty straightforward. Anytime you want to go down a line, you would add 160 bytes. And it, like I said, it's linearly mapped. And all you have to worry about is what colors you want in your palette and what you want to draw on the screen. So it's actually one of the simpler graphics modes I can think of for some of these older computers. Okay, let's look at our program again real fast that cleared the screen, because I want to point something out. Sorry, we'll go back to bank 0. Okay, so like I said, to set 16-bit mode, you actually need to first set the native mode in the processor by clearing carry and exchanging carry with emulation. So the emulation bit gets cleared, putting it in native mode. Then we set into a 16-bit accumulator and index register. And then this actually is kind of not what we wrote, right? We wrote to load into A a 2-byte value 0000, and we did not have a break instruction in here. So what happened here is that it's still doing the disassembly using an 8-bit accumulator. So even though it let us write it correctly, it's not really following along. It doesn't know what our code is doing. And you know, that can actually even happen with an assembler, so not just this mini assembler. So if you look up here, it shows that the accumulator right now, it thinks is set to 1, meaning 8-bit, and the same for the index registers. So I believe it's this way. You set 0 and you have to use a lowercase m. Okay, now it shows LDA with the 2-byte value 0000. But this one is now messed up, LDX. That's because we did not set X. we do the same thing, 0 equals x. All right, now it shows everything correctly. So this is just something to be aware of. If you're using the mini assembler, you might have to change between the 8-bit and 16-bit accumulator and X and Y index registers using those two settings. Likewise, you can do it with a language card bank. It's 0 equals capital L. But we typically don't need to worry too much about the language bank when we're writing Apple IIgs software from GSOS. You can also do it for the emulation bit, and I believe it's just 0 equals E, which it's not shown here, but it would be shown if I did the break. So now you can see the disassembly completely, and it looks correct here. Except for when, of course, we switch back to 8-bit mode here, and it shows this as a 16-bit value, so then you would need to switch back. And that's a little bit of a pain, and that's one of the reasons that we're probably going to move away from using the mini assembler after this week's lesson. So here you can see when I switch it back to 8-bit accumulator, there's our load C1 and turning on the super high-res graphics mode. All right, so next. Okay, we're going to do some animation, and this might be a little hard to follow because we're still using the mini assembler. So all of the branching and things like that might not make much sense without labels to help identify what we're doing, but I'll try and make it clear. For that reason, this is probably the last time we'll use the mini assembler in our projects. It's just getting too complicated. But it's a good skill to have, and it's good to know how to use the mini assembler because it also helps with disassembly and debugging. One problem with using it is if you are writing a program and your computer crashes, that program goes away. You can use AppleSoft Basic to save, any portion of memory by doing a binary save, and then you can say I want to give it a name like program and tell it where your program is located. So if I did something like that, oops, that's an L $100. So I'm saying save the 100 bytes at location 300 to a file named program. And if I type cat, you can see there's a file named program that's now filled with the contents of what was at 300. So I actually made two little basic programs, a loader and a saver, just so I can do little snapshots for this last experiment, because if I lose my progress, it's going to take me too long to really have the motivation to rewrite it. So I'll show you one of those real quick. The save one is basically just a basic program that does that for me. So I can just remember to, anytime I want to save my program, I can do that. And then when I want to load it back, I can just run load mini. Okay, I'm not going to do that right now. So let's write our program to do some animation. Like I said, this might be a little bit more complex, so a little harder to follow. We're going to write it all in native 65816 mode, but we'll be switching back and forth between the 16-bit and 8-bit accumulator and X registers. So we'll start at 300 again, and the first thing we want to do is turn on native mode, so we clear the carry, exchange the carry flag with the emulation flag. So now the emulation flag is clear, meaning it is not in emulation mode, it is in native mode, full 65816. Now if we were running in GSOS, who knows, I guess, where we would have started from, but starting from basic as it is, we're starting in an 8-bit mode. So I'm actually going to set to 8 bits first because I want to just write an 8-bit value real quickly to our new video register to turn on the super high-res graphics screen like we did before. And then I'm going to go back into full 16-bit mode. And I'm going to go ahead and set up two variables. I'm going to use 3FC for a direction variable, these 2 bytes. So it'll be, I'll set it to 0 if we're going left, and 1 if we're going to go right for our animation. We're going to move a bar across the screen. And then I'm going to use 3FE and F, basically these 2 values. I'm going to use this as our X index. And so it's going to be a value between basically 0 and 159.
Why 160 values? Because remember there's 320 columns of pixels on the screen, but each pixel is only one nibble. It's a value between 0 and f, so a byte holds 2 pixels. So 320 pixels is only 160 bytes, and I'm just going to do the byte indexing for now. We'll talk about how you would do the those sort of shifted graphics on the odd pixels later on. So going back up to, we had set the full 16-bit mode, and I'm going to initialize my variables here. I'm going to start this with the direction going right and our location at 0. So back at, this would be 30A, 30B, so we're at 30C now. And what I want to do is set my direction to right. Remember, I decided that 1 is going to be right, 0 is going to be left. I'm just going to toggle back and forth between that. And I'm going to store that at 3FC. And I'll load A with 0. And remember to use all 4 because the mini assembler doesn't know if you're in 8 or 16-bit mode. If you put in a byte, it's going to compile it, assemble it as a byte opcode. If you put in 2 bytes, a word, a 16-bit, word value, it's going to assemble it as the longer opcode. So I'm going to store that in our X position value, which I said was going to be 3FE. Okay, so we've kind of got our graphics screen on. We've initialized the position and direction for this bar that I'm going to draw. So the next thing we really need to do is clear the screen. And normally you would put this in a subroutine. I'm just kind of writing all of this in line. I know that A is still 0 from just loading it prior to this store. So I'm going to use that and also load X to 0. And yes, I could have written that differently, but and what I want to do is the same thing we did before. We're going to store it at our graphics location. And again, it knows to assemble that as a 24-bit address because I put in the full address there. So that stores at the screen. We can increment our counter because we want to write over the next pixel too, but since we're using 2 bytes at a time, we can increment by 2. And of course we'll compare to make sure we haven't hit the end of the palette data area. And if not, then we just continue storing again back here at 31B. Let's test this real fast before we go any further. And what it should do now is turn on the graphics screen and clear the screen. I'll do a set carry, an exchange carry with emulation, just to return it to emulation mode before I return. I'll try that. Okay, that worked. So turn my text screen back on. And that is not very easy to see in 8-bit mode, so don't forget to turn it to 16-bit mode when you're trying to look at the 16-bit code that you've written. We switch around a little bit here between 8 and 16-bit, but it happens to line back up on this one, and that's not always the case depending on your assembly. So, of course, eventually we'll probably be writing more in purely a 16-bit native mode, but some of these registers it's easier just to switch back to 8 and store your byte. Alright, so we've cleared the screen and then we returned here. So now instead of returning, let's go ahead and set up a palette. We know that we've already set all the colors to 0 and the palette data starts at 9E00 in bank E1. So let me see, line 3, 2, sorry. So at memory location 326, we'll overwrite this and continue our program. So I'm going to load 0FFF. And this might make a little more sense now to see it this way. This is your red, green, and blue value. And of course this part isn't used. So it's actually fairly straightforward when you're writing the assembly. Of course when you're looking at the hex data, these will be swapped and it might not make as much sense, like my earlier example where I was just poking values into memory. So that's the value for white. I'm going to leave color 0 as black, and I'm going to store this as color 1. So of course that's actually at location 2 because it's 0, 1, 2. This is 2 bytes. The first one was 2 bytes.
Oops, sorry, that is 9E02 is where the palette data is located, 9E00. Okay, so now we have our white color. Now let's write our main loop. And in our main loop, what we're going to do is undraw a line, basically draw it as black, update the position, move it left or right, and then draw it again. So in that way, it'll look like basically a line is kind of sliding across the screen. And when it hits one edge, we'll bring it back to the other side. First, I'm going to write my line drawing routine. I'll just kind of stick this up higher in memory. So we'll make this routine that we can call with A holding the word that we want to store on the screen, and X holding the X position that we want to store it at. And to draw it from the top to the bottom, I'm just going to keep track of what line we're on using the Y register. So I can already I initialized the Y to start at line 0. Now we're going to start storing our data to the screen, our pixel data. Now I want to add 160 to X to get to the next line. Remember, 320 pixels is 160 bytes, so to get to the next line of the screen beneath this, I need to add 160 here, but we can't do math operations with an index register. We have to move it back to the accumulator. So I'll use push A to the stack to basically stash that while I do some math. Transfer X into A. So now X has been copied into A, and I can do my addition. So we prepare for addition by clearing carry. Then we add with carry. Again, remember to use the 16-bit 00A0 here to add 160. If you just put A0, this will compile incorrectly and your program will crash. Okay, so we've now added 160 to our X value. We're going to transfer it from the accumulator back to the X register. And of course we need to get our color value back off the stack so we don't have a stack overflow. Alright, now that we've done that, we basically updated all the pointers to the next line. So I'm going to increment my counter variable here and make sure that we have not hit 200 lines yet. So what is 200? Oops, did that backwards. Equals 200 is C8. Remember, we've got a little built-in converter. 39F, that puts me at 3A0. 3A0 for my next instruction. I'm going to compare Y to the 16-bit value C8. And if we haven't hit it yet, then I am good to go back to the drawing portion of the loop, back up here at 393. Remember, we've already updated X, so it's already pointing at the next place to draw. And what would basically happen is the last iteration of this loop will actually point this X past the screen, past the pixel values, meaning it would run into some of the other values. So you don't want to do that, which is why we stop here. But just letting you know that it's not a good thing to store outside of the pixel data if you're not trying to draw. Alright, now again we just branch up to 393, yes. If we're not done drawing the line, if we have, then we've gone past and we don't need to draw anything, so we can just return. So that's our line drawing routine. Let's go look at our main program again, and here's where we set our palette color, which leaves us here. I'm just going to test this routine real quick. So at 3, 2D, I'm going to try and load the color 1111. So that should be all white because we just set the color in palette 0 to white. I'm going to load X, the number 5. So that would actually be, what, 10 pixels on the screen to the right. And then we will try our new routine at 390. And then I'll just return again. Just in case, I'm going to run that saver in case I happen to crash something here. I don't know what's going to happen. Okay, well that was good. It actually drew our white line on the screen, and this is actually 4 pixels wide because we drew 1, 1, 1, 1, and remember we set the color 1 to white. And so I just did that all the way down the screen by adding 160 each time and keeping track of the Y register, and when I hit 200 I said okay, I'm done drawing. So back again, set our 16-bit. So it's kind of a bad break there. I'm going to list from 326 here where we set our palette color. Okay, so we set our palette color, and then we did our little drawing test by setting the parameters for our routine and then calling it. So now instead I'm going to just create a little logic there that we'll do our main loop where basically we're going to undraw the line by drawing black using whatever value is in our 3FE location. Then I'll update the position and then draw white. We are going to start right here at 32D. And what we're going to do now is load into X. We're going to call our subroutine again the position of X, which remember is 3FE. And we're going to load into A the pixel data 0000, so 4 black pixels in this case, and jump to our subroutine. So that was easy. We've just undrawn our line. Now is the slightly harder part. We're going to look at the direction variable and update our X position based on that. And then after we're done with that, we'll draw the white line. We load the direction, remember 3F, C, and D. I've already kind of done some pre-compilation here, so I know the spacing on this, and this is where it's hard to do this with a mini assembler. I would pick some value way up further in memory, but I already know that this is going to come out to a certain length. So we've loaded the direction, and I'm going to branch if it's not equal. So that means if it's right, I'm going to have to branch somewhere. And in this case, I'm going to branch to 34B. So that's basically my right subroutine, which means we're now in the left subroutine because we didn't branch. So for the left subroutine, I'm just going to decrement our X position in memory, and I'm going to load that real quickly. Actually, I don't even think I need to do that to condition the 0 flag. But oh well, this works fine. So I load it, and now I'm going to branch past all this. I'll put this at 360. We'll kind of skip ahead. So 360 is where we're going to draw our white line. So if I decremented it and I haven't hit 0, I decremented our X position, I load it. If it's not 0, then we haven't hit the left edge yet. We're still moving to the left, because remember, this is my left subroutine. So I'm going to go to my draw, the next part where we're going to draw the white line. I'm just going to put that at 360. That should be enough space to finish up this little section of logic that updates the current X position. If we did hit the left side, then we're going to have to go ahead and change our direction. Remember, 1 is right, we're going left. So I'm going to store that in our direction variable, 3FC and 3FE. And that's it. I'm going to skip ahead because we don't want to run into where I was going to put that right routine. So we're going to branch ahead to that same 360 because we're ready to draw. All I had to do was change directions when I hit 0. And magically I'm landed right here at 34B, so this is going to be our right subroutine. And in this case, we kind of do the opposite of what we did before. We increment our X position, and actually do need to load it for this one, and compare it to our max value. So our max value should basically be 160, but remember our data is 4 pixels wide, so we would take off 1 for the 1 byte, but we actually need to take off 2 because it's 2 bytes wide. So that is 9F, 9E, right? So if we are at 9E, that should be somewhere right here, and we're going to draw on these last 2 pixels. And If we haven't hit that, then we're done here like before. We've just slid to the right, but we're not at the right edge. Then we can just go ahead to our 360 again, where we're going to draw the white line. Otherwise, I need to switch our direction. I can just use the store 0, which we haven't really talked about, but saves you some trouble. You don't have to load the accumulator. You can store 0 just directly using a store 0 command. And we'll store that in the direction variable to go left. And there's some space left, so I'm going to have to branch always up to where I decided I was going to put my drawing stuff. Okay, so there's a little gap there. Now, to draw the line, it is basically like we did before with the black line, except instead of drawing with zeros, we're going to load ones like we did in our first little part of this demo. So we load 1, we load into X our newly calculated X position, call our draw line routine. We'll do one other thing here. So we would branch up to the beginning, just do that over and over. I'm going to go ahead and put in a key check real fast so that we can return if somebody hits a key. So to do that, I'm going to switch back. So this is the end of our loop basically, and I'm just doing one quick check before we finish our loop to say, did they hit a key? If so, we can quit. I'm going to go back to 8-bit mode and just load the same key location that many Apple II users are familiar with, bank 0, location C000. If there is, if the high bit is not set, there's not been a key press. So I'm going to jump ahead a couple of bytes here to 37B, and then if there is a key press, you're supposed to clear the keyboard using this strobe. And I'm going to go ahead and be nice and turn off the graphics screen, and then return to monitor in 8-bit mode. Actually, I kind of messed up. This is, I suppose, more proper, but I'm already over 37B. I need to make this smaller, so I'm just going to leave off these 24-bit addresses here. I don't really need them. It'll make my code fit in the space that I had kind of allotted for it. So let me redo that as the shorter 8-bit addresses. Again, if we don't have a key, we skip ahead. If we do get a key, we clear the keyboard strobe. And turn off the graphics screen. Sorry. And then we can basically return to emulation mode and return to the monitor or the calling program. Oh, let me, still one byte over. Whoops, I'll redo. I don't need a bank here. Just trying to kind of be explicit, but okay, so now at 37B, I've got enough space. This is if we didn't get a key, and we're just going to branch up to our main loop. So at 37B, what is our main loop? It starts right here. Remember, after we set the palette color, we load our X value and undraw that last line that we did. So we're going to branch back up to 32D. So where was the end of all of this? At 37B, branch to our main loop at 32D. And hopefully with the
key check I put in there, we can gracefully exit now. But just in case, I'm going to save again. Did not like that. Oh, yes, I made a classic mistake. I was at the end there, and I was going to branch back up after doing this key check, but you'll notice I did the SEP30 here, and I never went back into 16-bit mode, which this entire loop expects to be. So we're still in native mode. We just need to set the long accumulator and long X, and then we can branch to 32D. And great. Now, obviously, even though this isn't an emulator, you can see some weird video stuff, and this would be happening even on a 2GS. I'll change the speed of the emulator. This is at 8 megahertz. This is at 1 megahertz, so slower, but what's happening is that it's undrawing and drawing so fast that it's really just kind of creating this flickery, torn animation. So back to 2.5 megahertz. And our key check worked, so that's good. In the document I talked about earlier, and of course in the either the firmware or the hardware reference, there's information about the vertical blank flag on the Apple IIgs. And remember earlier we read that horizontal and vertical counter position. This one just tells you whether or not it's in vertical blank or not. So if it's in vertical blank, it means it's somewhere between lower right and top left, and it's moving its way back. If it's not in vertical blank, that means it is drawing somewhere on the screen. Okay. There's different ways to implement your vertical blank weights. We'll talk about some different ones as we go along, including some that don't use this register at all, but use some of the vertical counter tricks that we learned earlier. But for now, we're basically just going to put in a quick vertical blank weight. So at the end of our loop, we draw our white line, and then we're going to wait until we get into vertical blank mode where we're not drawing anything. Then we're going to try and very quickly erase the white line with a black line and then draw the new white line. So let's do that. We can just add that code in right where at the end where we had the key check. So here's where I fixed my bug earlier. We're going to overwrite this because I'm going to need it to stay in 8-bit mode a little bit longer just to read that 8-bit register. I don't have to, but since I'm already there, it's easier to do that and just not have to mask off any data. So at 37B, I want to load C019. And basically, if we're not in vertical retrace mode, we wait. And once we are in vertical retrace mode, then we'll switch back to 16-bit mode and branch back to the main loop where we're going to undraw. Let's see if that makes any difference. And sure enough, the animation may look like it's skipping a few frames here and there, but it shouldn't be on a real system. It should be time consistent. There's not really much to this loop that changes. I mean, there shouldn't be much of anything except for the direction stuff. So that's at 2 megahertz. Here it is at 8. Which it's possible that it's actually getting in 2 updates or something per vertical refresh. And then back at 1, you can see what's happening here is that we are not finishing our animation in time. So it doesn't work at the slow speed, but at the real speed and everything, we've just kind of created our first animation. I know that was a lot of trouble, and like I said, we'll move on from the mini assembler from here, but you can do this stuff in mini assembler. And again, Control C to exit out of here. You can, oh, well, apparently my basic is somehow corrupted. I think I messed it up when I accidentally did that crash earlier when I was in 8-bit mode, and I should have switched back to 16-bit mode. So that's some animation. I wanted to go into drawing some sprites and stuff like that, but I think we really need to take a break from the fun stuff of drawing on the screen and move our way into an assembler environment where you guys can have labels, and it'll make a lot more sense and the code will be a lot easier to read. We'll just have to start dealing with the actual assembly step instead of this sort of real-time assembly, which is great for interactive learning, but it's getting harder and harder for me to manage and to keep in my head, so might not be the best thing. Alright, I hope you learned something today about the super high-res graphics stuff, and don't forget to check out the document on the GitHub page that I talked about. It's really a great cheat sheet for all the memory locations, and I would just print it out, and I should have said that at the beginning. I would print it out and keep it next to you while you're working on your programs. It's really invaluable, unless you have the reference manuals open to those pages, but I think mine is compressed into an even smaller space, so I really like having it nearby. Alright, that's it. Thanks for watching.